All right, let's dive in. Today, we are going under the hood of artificial intelligence to see how it really thinks. We're going to trace the entire path from the moment you type a question to the second an AI generates its answer. It's going to be a fun ride. You probably use these tools all the time, right? But what's actually happening inside that digital black box? I mean, how does a machine take a bunch of your words and turn them into a coherent, sometimes surprisingly creative answer? That's exactly what we are going to unpack. So, first things first, let's get on the same page. At the heart of all this is what we call a large language model, or an LLM for short. Just imagine a massive, insanely complex system that's been trained on a library basically the size of the entire internet. Its whole job is to learn the patterns of human language so well that it can speak it right back to us. Okay, so the whole process kicks off the second you hit enter. But here's the thing, the model doesn't see words the way you and I do. So the very first step is to translate our human language into something a machine can actually work with. It all starts with something called tokenization. Yeah, before the AI can understand a single thing you've written, it has to chop your sentence up into these little manageable pieces called tokens. Seriously, think of it like dicing up vegetables before you start cooking. These tokens can be whole words, or as we're about to see, even smaller bits of words. For instance, a super common word like the might just be a single token. Easy enough. But a more complex word like artificial could get broken down into smaller subwords like art, ific, and eel. And this is actually a really crucial trick, because it lets the model handle a massive vocabulary, even words it's never seen before, without getting completely confused. So once we have all our tokens, the next step is to give them meaning. And this is where something called embeddings come in. Each and every token gets converted into a really long list of numbers, a vector, which basically represents its address in this huge mathematical space. So words with similar meanings, like king and queen, will have addresses that are really close to each other. This is how the model starts to grasp not just words, but the relationships between them. So now your prompt has been turned into a bunch of meaningful numbers. It's ready to enter the core of the LLM, the neural network itself. And the architecture that completely revolutionized this whole field is called the transformer. So why was the transformer such a massive game changer? Well, you have to remember, older models had to read a sentence literally word by word. It was slow, and they'd often forget what was said at the beginning of a long paragraph. Transformers are different. They look at all the words, every single token at the exact same time. This means they can draw connections between a word at the start and another at the very end, and they use this clever trick called positional encodings to remember the original word order. And the superpower that lets transformers do all this is called the attention mechanism. It is a brilliant idea. It basically lets the model decide which other words in your prompt are the most important for understanding any single word. It's how the model builds a really rich, deep picture of context. Let's take a super simple sentence. The cat chased the mouse. The attention mechanism lets the model see that the word chased is fundamentally connected to both cat and mouse. It learns to pay less attention to words like the and instead focus on the key relationships that give the sentence its actual meaning. Of course, there's a limit to this. The model can't process an infinite amount of information all at once. That limit is called the context window. You can think of it as the model's short-term memory. Now, a bigger window means it can read longer documents and have more complex conversations, but it also takes way more computational horsepower. Okay, so the model has processed your prompt, it gets it. Now it has to generate an answer. And this is where things get really cool, because the model isn't just searching a database for an answer, it's building the response from scratch, one token at a time. Now, one of the main controls we have over this process is a setting called temperature. The easiest way to think about this is like a creativity dial. You're basically telling the model how much randomness it's allowed to inject when it's picking the very next word for its response. And this creates a really fascinating trade-off. See, if you turn that temperature dial way down low, the model plays it safe. It'll always pick the most predictable, highest probability next word. This is perfect if you want a factual answer or a straightforward summary. But when you crank the temperature up, you're dialing up the randomness. The model starts taking more risks, picking less obvious words. This leads to more creative, diverse, and sometimes really surprising results, which is exactly what you want for brainstorming or storytelling. Now, besides temperature, there are other ways the model can choose that next token. There's top case sampling, where it only considers, say, the top 20 most likely options. Or there's top P sampling, which is a bit more flexible and picks from a pool of words that add up to a certain probability. Really, these are just more dials developers can turn to shape the AI's voice and personality. So, a base model out of the box is incredibly powerful, but that is not the end of the story. Developers use some really sophisticated techniques to make these models even smarter, more accurate, and a lot more useful for specific things. Let's take a look. The first method is actually something anyone can do. It's called prompt engineering. It's really the art and science of how you write your input. Just by changing how you ask a question or the instructions you give, you can dramatically improve the quality of the answer you get back. It's all about learning how to speak the model's language to get exactly what you're looking for. For even better accuracy, developers use a technique called retrieval augmented generation, or just RAG. What happens here is, before the AI answers your question, it first goes out and searches an external up-to-date knowledge base, like a company's internal wiki or recent news articles. It then uses that fresh information as context to generate its answer. This is huge because it massively reduces errors and makes sure the info isn't stale. And what if you want to specialize a model for a totally new task? Well, retraining a giant billion-parameter model from scratch is unbelievably expensive. So instead, we have techniques like LoRA. LoRA lets developers adapt just a tiny fraction of the model's parameters. This makes fine-tuning so much more efficient and accessible for everyone. Of course, for all this incredible power, these models are not perfect. We're still facing some pretty big challenges. These systems take a massive amount of resources to run. They can accidentally pick up and even amplify the biases from their training data. Their black box nature can make it really hard to understand why they give a certain answer. And of course, privacy is always a major concern. Solving these problems is the next great frontier for AI research. So there you have it. We've gone from your prompt, to tokens, to embeddings, straight through the transformer's attention mechanism, and out into a generative response shaped by temperature and sampling. We've taken a real peek inside the engine. I guess the only question left is, where do we want it to take us?